Assalamu alaikum. My dear cadets of class 12, I welcome all of you to my online physics class of Borishal Cadet College. During this ominous cloud of COVID-19, you were not able to stay at your second home. So our academic program is being hampered. That's why this online effort that has been taken by the authority of Borishal Cadet College to carry on our learning process. My dear cadets, during this corona outbreak, please don't go outside of your home. Please stay home, stay safe. Before starting my class, I would like to introduce myself. This is Mr. Kamruzzaman Khan, lecturer, Department of Physics, Borishal Cadet College. This class for class 12 cadets, subject physics, chapter 8. Name of our today's chapter is modern physics. Okay, my dear cadets, observe this picture and try to guess what should be our today's lesson. Today's topics, yes, we're going to start relativity. Along with this topic, I will discuss reference frame, relativity, that is special theory of relativity, general theory of relativity, Galilean transformation, Lorentz transformation, time dilation, and length contraction. Learning outcomes of my today's lesson. By the end of my today's discussion, cadets will be able to explain the concept of modern physics, explain the inertial and non-inertial reference frame, analyze the result of Michelson-Morley experiment, explain the theory of relativity of Einstein, explain Galilean and Lorentz transformation, and describe time dilation and length contraction. Key points of my today's discussion: reference frame, inertial reference frame, non-inertial reference frame, special theory of relativity, general theory of relativity, Galilean transformation, Lorentz transformation, time dilation, and length contraction. Let's have a closer look towards the discussion about relativity. Before starting relativity, we have to know what is the initial concept of our scientist. According to the classical mechanics that has been established by Newton, Newton considered space-time and mass are absolute or independent, but nowadays we know it very well that space-time and mass are not absolute or independent, but rather they are dependent. According to Einstein, space-time, mass are not constant, but they are relative. This is called Einstein's theory of relativity. Absolute means not variable with respect to anything. According to the special theory of relativity, absolute motion is meaningless. All motions are relative. Dear boys, we have to know the relative motion before starting relativity. Suppose if one of the two trains standing side by side in a station starts moving, then to a passenger in this moving train will appear that the other train has started moving in opposite direction. This happens due to the mutual motions of the train. This apparent motion of the static train to the moving passenger is relative motion. Even the nature and the path of the relative motion of a body may different depending on the reference frame. As for example, let us consider a train moving with uniform velocity. A passenger sitting on the train just drops a stone through the window. He will see that the stone drops vertically downwards. but an observer standing beside the train will notice that the stone drops in a parabolic path. So from this discussion, we can say that no motion or anything cannot be absolute, but each and everything is relative. Types of theory of relativity. There are two types of theory of relativity: general theory of relativity and the special theory of relativity. General theory of relativity. The general theory of relativity deals with the object or system having accelerated as well as uniform motion with respect to one another. For example, motion of the sun, moon, stars, comets, etc. The laws of dynamics and the relativistic concept of space-time, mass, and the conclusion that is deduced from these laws and concepts are known as theory of relativity, and this is also known as the special theory of relativity. Now, we are going to discuss about the frame of reference. What is frame of reference? The coordinate systems in respect of which the position of an object can be determined is called frame of reference. Frame of reference, there are two types of frame of reference. Before starting the types of frames of reference, we have to know what is frame of reference. Suppose you are staying at Borishal Cadet College. It is my questions to know where is your location. Let's have a discussion. Borishal Cadet College is very nearby of Borishal. In Borishal, there are many places such as Natullabad, Bibirpukur, Rupatoli, etc. Your position will be different when it will be measured from Natullabad, Bibirpukur or Rupatoli. So we need a very definite point so that your location will be very conducive for me. That's why every city must have 0 point. Every distance is measured from this 0 point, and this 0 point is called reference point. Now, you can say that you are 20 kilometers away from this Borishal city or point of reference. So, boys, such a type of frame of reference is very helpful to determine the position or motion of any object. Okay, boys. Now I'm going to discuss about types of reference frame. There are two types of reference frame: inertial reference frame and non-inertial reference frame. Any frame of reference that moves at constant velocity relative to an inertial frame is itself an inertial frame. There is no acceleration in that inertial frame of reference. And non-inertial frame, any frame of reference that does not move at constant velocity relative to an inertial frame, is itself an non-inertial frame of reference, and there must have somewhat acceleration. Okay, boys, let me clear what is the condition for inertial frame of reference and non-inertial frame of reference. Suppose you are in a lift. When this lift starts to move, it must attain somewhat acceleration. After some time of moving, this lift will be able to move with constant velocity, and this is the condition for inertial frame of reference. And when this lift try to stop, it will lose its constant motion. That's why you will feel weightlessness, and this is comparable with non-inertial frame of reference. Okay, now postulates of special theory of relativity. There are two postulates of special theory of relativity that are as below. The laws of physics are the same in all inertial frames of reference. And number two, the speed of light in free space or vacuum has the same value in all inertial frames of reference. Now I'm going to discuss about the transformation. Transformation means how much the measurement of a reference frame will be changed with respect to another reference frame. Transformation is the relation of measurement between an inertial frame of reference to another inertial frame of reference. And there is very conventional reference or transformation, that is Galilean transformation. Now we are going to see what is Galilean transformation. It is used to transform between the coordinates of two reference frames which differ only by constant relative motion within the construction of Newtonian physics. That is, Galilean transformation is based on the Newtonian mechanics. Okay, now we are going to see the Galilean transformation in details. Galilean transformation, let us suppose there are two inertial reference frame, that is S frame and S prime frame, and this is the observer of S frame and this is the observer of S prime frame. And let us suppose S prime frame is moving away along x-axis with constant speed v with respect to the reference frame of S. Let an event, what is the event? Event is the combination of position and time. Suppose an event occurs at point P, and this event is called the flying of butterfly here. Suppose an observer from S frame observe the coordinates of the occurrence of event as x, y, z in time t, that is x and y and z and in time t. And an observer from S prime frame the coordinates of occurrence of the event as x prime, y prime, and z prime and t prime. Now we are going to see the relation between x, y, z, t, and x prime, y prime, z prime, and t prime. Suppose that when the origins of frames S and S prime coincide, then the clock of both the frames starts. That is, there are two clocks. This is the first clock of S frame and this is the clock of S prime frame. And to measure the event or measure the connection between the transformation of an event, we have to synchronize the two clock of that two frames. As S prime covers a distance Vt in time t, S prime covers a distance from S frame, that is Vt. So the measurement taken in S frame along X axis exceeds those measurement in S prime by the amount of Vt. Now we are seeing that the position of butterfly is x prime meter away from this observer of S prime, and it is Vt plus x prime away from the observer of S. Now we are going to establish a relation between these two measurements. What is this? It is very much clear that the measurement by S prime frame is x prime is equal to x minus Vt, and this is the Galilean transformation of position. Now the Galilean transformation of height, or that is Galilean transformation of x prime is equal to, y prime is equal to y, and z prime is equal to z, and t prime is equal to t. Here it is very much clear that the time interval is t prime is equal to t, and this is the very strong limitation of Galilean transformation. And it is, according to our modern physics, it is very much clear that the time that is measured for two different frame of reference will be different, will not be same. Now for limitation of Galilean transformation. The first limitation of Galilean transformation is all the equations of Newtonian mechanics remain unchanged in the Galilean transformation, but the laws of electromagnetic theory do not remain unchanged. For second limitation of Galilean transformation, the speed of light in free space or vacuum has not the same value in all inertial frame of reference. We know from the postulate of Einstein that the speed of light in free space or vacuum should be same from all inertial frame of reference. Okay, boys, let's see the limitation of Galilean transformation. From the Galilean transformation, we can write Vb prime is equal to Vb minus V. Vb prime means the velocity that is measured from S prime observer is equal to velocity that is measured from S observer minus the velocity that have the frame. Let the velocity of light from S frame is c, and the velocity of light that is measured from S prime frame is c prime. If the velocity of frame is c by 2, then we can write according to the Galilean transformation of velocity, c prime is equal to c minus c by 2. So here is the difference. The velocity that is measured from the S prime frame is c, and the velocity that is measured from S prime frame is c prime. And according to the Galilean transform, according to the Einstein's postulate, the velocity that is measured from these two observers should be equal, but here is difference. The velocity that is measured from S prime frame that is equal to c by 2, but it is supposed to c prime is equal to c, which is the violation of Einstein's postulates. Next, the Lorentz transformations. Lorentz transformation is the special set of linear transformation that preserves the constancy of the speed of light between inertial observers and account for the problem of simultaneity between these observers is known as the Lorentz transformations equations. Okay, from our Galilean transformation, we have seen that the speed of light that is measured from different inertial frame of reference should be different, but it is supposed to get the same speed of light from all inertial frame of reference. So it is very obligatory to find a special transformation from where the measurement of light should be equal. That is, measurement of velocity of light should be equal. That's why this management. Okay, let's see the Lorentz transformation of position and time with respect to S frame. Okay, boys, we have seen from our Galilean transformation here, x prime is equal to x minus vt, but this is very different case. Here, extra term is added, that is k. Okay, this time for Lorentz transformations. The special set of linear transformation that preserves the constancy of the speed of light between inertial observers and account for the problem of simultaneity between these observers is known as the Lorentz transformations equations. Okay. From the discussion of Galilean transformation, it is very much clear that the speed of light that is measured from different inertial frame of reference should be different, but it is supposed to get same velocity of light from all inertial frame of reference. That's why this management, and it is very mandatory to find out the spatial transformation, and it is our Lorentz transformation. Let's see the Lorentz transformation. Lorentz transformation of position and time with respect to S prime frame, that is S prime x prime is equal to k x minus vt is equal to x minus vt divided by root over 1 minus v square by c square. Twice. You have seen that that is Galilean transform. According to the Galilean transformation, x prime is equal to x minus bt, but here is multiplied an extra term, that is k, and the value of k is 1 upon root over 1 minus v square by c square, and that's why we can write this is x minus bt root over 1 minus v square by c square. Here t prime is equal to t minus vx by c square over root over 1 minus v square by c square, and it is got from this from the calculation of x prime. Now inverse Lorentz transformation of position and time with respect to S frame, and this is x is equal to k x prime minus x prime plus vt, and t is equal to t prime plus vx prime divided by c square root over 1 minus v square by c square. And this position, that is Lorentz transformation of position and time, is got from Hughes calculation, but we are avoiding this Hughes calculation. Now let us suppose this Lorentz transformation is true. Now let's see the verification. Before verified the statement of postulate of Einstein, we have to know Lorentz transformation of change of position and time from S prime frame. Here del x prime is equal to del x minus v del t divided by root over 1 minus v square by c square, and del t prime is equal to del t minus v del x divided by c square root over 1 minus v square by c square. And you have seen this transformation from Galilean transformation. Okay, transformation of velocity from S prime frame. Velocity is the change of position, so velocity from S prime frame is equal to x prime 2 minus x prime 1 divided by t prime 2 minus t prime 1, that is del x prime divided by del t prime, and that should be equal to del x minus v del t divided by root over 1 minus v square by c square, and over del t minus v del x by c square divided by root over 1 minus v square by c square. After this Hughes calculation, we can write very easily del x minus v del t divided by del t minus v del x by c square, and this is the transformation of velocity from the observation of S prime frame, and dividing this by del t, and we are getting vb prime is equal to vb minus v divided by 1 minus vb divided by c square. Okay, now this is very interesting part, justification of Lorentz transformation. According to the postulate, that is second postulate of Einstein, velocity of light should be equal. So let's see. Let us suppose there are two observers from S and S prime frame, and here a flashlight is going on with somewhat velocity. Let this velocity that is measured from the S prime frame is Vb prime is equal to C prime, and the velocity of light from S prime is equal to Vb is equal to C. Now, according to the transformation of velocity of Lorentz transformation, we can write Vb prime is equal to Vb minus V divided by 1 minus Vb divided by C square. Now, we are putting the value of Vb, that is Vb is replaced by C, and V is the velocity of the frame of reference, that is S prime frame. And now we are putting the value of Vb, that is here Vb is C, and V the velocity of S prime frame, and C square is C square. Now after calculation, we are getting C prime is equal to C. Yes boys, we are getting the very justified transformation, that is Lorentz transformation, and according to this Lorentz transformation, velocity of light that is measured from different inertial reference frame is same, so it is right. Okay, Lorentz transformation is verified and it goes with Einstein's theory. Lorentz transformation is same to Galilean transformation for very low velocity, but for very high velocity, Lorentz transformation and Galilean transformation is not same. Okay, boys, let's see the time dilation, and it is very interesting matter of special theory of relativity. What is time dilation? An interval of time observed in a moving frame of reference will be less than the same interval of time observed in a stationary frame of reference, that is called time dilation. And this famous equation is T is equal to T naught divided by root over 1 minus B square by C square. But I think this equation you will not get. Okay, let's see the explanation. Let us suppose there are two frame of reference, S frame and S prime frames. These two frames is inertial frame. Here an observer is reading a book, that is physics books. He starts to read this book at T1 prime and finished it T2 prime. So time interval is del T is equal to del T prime. Now this event that is happened in S prime frame is observed from the observer of S frame. According the observer of S frame, the time interval of that event becomes del T is equal to T2 minus Q1. Now let's see. Lorentz transformation of change of time of two event is equal to del T, that is del T is equal to del T prime minus V del X prime divided by root over 1 minus B square by C square. And in S prime frame there are two events, time interval of these two event is like that, and this time interval of the two events from S prime is like that. So del T is proper time because del X prime is not changed with respect to the observer of S prime. What is proper time? Yes, we should tell it proper time because the event that is happened in S prime frame is not changed with respect to the observer of S prime frame, but the position of this observer is changed with respect to the observer of S frame. So the time that is measured by the observer of S frame is not proper time, but the time that is measured by the observer of S prime frame is proper time. Now equation becomes del T is equal to del T prime minus V del X 0 divided by C square root over 1 minus V square by C square. Here del X is equal to 0. That's why this equation becomes del T is equal to del T prime divided by root over 1 minus V square by C square. And for our conducive, T is equal to T naught divided by root over 1 minus V square by C square. That is del T is replaced by T and del T prime is replaced by T naught. And from this equation, it is very much clear that this is the time, that is del T is the time that is measured from S prime, and T naught, that is del T prime, that is the time that is measured from S prime frame. So del T prime, that is T0 is proper time and T is not proper time. And here it is very much clear that T is very greater than T0. Okay, so this is called time dilation. That is the event that is happened in S prime frame will be slower than that of observed from the S prime frame. Sorry, S frame. Okay, boys. Let's see a stem. This stem is inserted here, and this is related stem of time dilation. Okay, you should try your level best, and the solution of D is given here, and it is very much important for you. Okay, boys, let's see the length contraction. This is the another interesting case of special theory of relativity. The length of a stationary object with respect to an observer in motion is shorter than the length measured by the observer in rest. That means faster means shorter. The equation of length contraction, L is equal to L naught into root over 1 minus B square by C square. Let's see the explanation. Here, there are two reference frame, that is inertial reference frame, that is denoted by S and S prime. The two observer from these two reference frame, according the observer of S frame, the length of the scale becomes del x prime is equal to x2 prime minus x1 prime, and the length of this scale is measured by the observer of S frame should be del x is equal to x2 minus x1. Okay. Lorentz transformation of change of position or length. According to the Lorentz transformation, del x prime is equal to del x minus v del t divided by root over 1 minus b square by c square. And in S prime frame, the length of the scale is like that. And from S prime, the length of the scale is like that. But time interval del t must be 0. Otherwise, the measurement that is measured from the S frame will not be accurate. Okay, boys, equation 1 becomes del x prime is equal to del x minus b del t divided by root over 1 minus b square by c square. Now, we are putting the value of del t is 0 and getting del x divided by root over 1 minus b square by c square. Here, del x prime is replaced by L naught, and L naught, that is del x prime, is the measurement of length from the observer of S prime. And this is the length of this scale, and it is called proper length because the position of this scale with respect to the observer of S prime frame is not changed. That's why it is called proper length. Okay, and now we are getting this equation L naught is equal to L divided by root over 1 minus b square by c square, and here L naught is greater than that of L, and this means the length of an object in moving state will be less than its length in static state. This phenomenon is known as Lorentz-Fitzgerald contraction. Now boys, let's see the types of questions. This is knowledge-based questions that is based on our today's discussion, and this is comprehension-based questions. Let's have a closer look towards these two types of questions. Now, application-based questions. Application-based questions is the combination of three questions. First, knowledge-based questions. This is knowledge-based questions. Second, comprehension-based questions. This is comprehension-based questions. And this is application-based questions. Let's see the higher order-based questions. This is the combination of four types questions. Along with these three types question of application-based, there is extra type questions, that is higher ability test, and D question is higher order based questions. Some sample MCQ. Here, the first MCQ is knowledge based MCQ, and second MCQ is comprehension based MCQ, and this is the STEM, and we are getting two types of MCQ here. This type of MCQ is called situation set based MCQ. Okay, boys, you should try a level best to understand these questions. Okay, boys, at a glance, what we have discussed today: Galilean transformation, Lorentz transformation, time dilation, and lastly, I have discussed length contraction. Let's see the home task. I have inserted here SCQ questions, and after solving these questions, you must submit this solution through our website. And this is home task, that is MCQ questions, and after solving these questions, you also submit this. Boys, if you have any query, please write in inbox. And I will try my level best to answer these questions in my question sessions or in my class. Dear boys, we're facing very tough situation, and today or tomorrow, inshallah, we'll get our very smooth life. So during this corona outbreak, please don't go outside of your home. Please stay home, stay safe. Thank you.